Welcome back to a Geek Warning bonus episode. My name is Ronan McLaughlin, and today I'm bringing you this extra episode in addition to our regular weekly show because I just had the opportunity to sit down with two key figures from the Colnago design team to explore some of the design processes and the thinking behind their new Aero bike, the Y1Rs. Davide Fumagalli is head of product at Colnago, and Torny Feldskjar is one of the lead designers, and both of them take us through every aspect of the Y1RS, how it came to be, and why both CFD and a relaxation of the UCI's frame design rules made all this possible. We discussed some of the challenges in balancing aero demands of a modern aero bike with rider comfort and how they intend to do so. We look at some of the testing that went into this bike, including, again, CFD, then wind tunnel validation, and then some of the structural and stiffness testing that they've done on the new bike. And finally, they tell me why any claims of X number of watts faster are all lies, which is an interesting take, but yeah, we'll get into that in a bit. Long story short, Davide and Torny explained to me how they balance data-driven design with real-world feedback from a World Tour team, and I try to grill them on how real all that is. Both were very open on their responses, and so I hope you enjoy this episode. And without further ado, let's get on with the show. Davide, Torny, welcome to the show. Thank you for joining us here today.
Thank you. It's a pleasure to be here.
Davide, you're head of product at Colnago. First time on the show here. Do you want to give us the listeners just a bit of an introduction and as to what you do at Colnago?
Yeah, big name for me, as I told you. I just have fun designing bikes and supervising my team, which is composed by six people all around the world, I would say. I've been in Colnago since 2009, so long time in the company, and it's always new to launch new products, to work on new bikes, so I'm having fun.
And you're a racer yourself at heart.
I once did, but less and less.
Yeah. Well, I know you've got a new addition to the family recently, but you were racing even gravel until recently.
Yeah. I think the last race I did was the Gravel World Championship, where I enjoyed the race. Let's say
you also did quite well.
Yeah.
Come on, tell us.
No, I got a medal.
Yes.
Let's say I was not completely happy with that, but it was fun.
Well, I think that's something you should talk more about. Getting a medal in the World Championships is always something good. Torny, listeners to the show might not be familiar with your voice, but they might be familiar with your work from our Joyrides features. You've had two bikes feature in that.
Yeah, a couple of custom hooligans, yeah. Correct?
Yes.
Yeah.
You've had a Seiko custom hooligan, and you've had a cargo take on a Cannondale also.
Right, yeah. So those are some fun little side projects.
And just give the listeners an idea, what is it that you do at Colnago also?
At Colnago, well, I work with Davide and his team to, on the industrial design, giving shape to the bikes, connecting the dots. We have all the constraints to work with, and all the aero sections and all the structural constraints, and we try to make the most of that, right? From a design point of view.
We hear industrial design. What is it that an industrial designer brings to a project like we're about to discuss today?
That's a good question. Traditionally, it was back in the day when I started out. I've been in this industry now for 20 years, and
some brands that people might. Cannondale, BMC, people will have seen your bikes before.
And a few years in automotive as well. And I think when I started out, it was more, the role was like you had almost a finished product, and our task was like, make it look pretty.
Okay.
Or
make it fit the design language of the brand.
Yeah, obviously. Yeah. Which and that role has changed. We're involved early on in the early stages now. Sometimes it can be, it depends a lot on what sort of bike it is, right? If it's a road bike that's going to be ridden in Tour de France, we have a very specific user case. If it's a city bike or if it's a gravel bike, it's very different, right? So it's about understanding the user case, I think, which is one of the reasons AI will not replace us anytime soon, like fully at least.
Okay.
And interpret sort of the needs of the customers or the riders, but to also try to come up with either following a certain design language that gives it sort of a brand feel and connection to the other products in the family, or sort of stake out a new course for a brand, right?
But you're working with Colnago for how long now?
3.5 years.
Okay.
Yeah,
Okay.
yeah. So V4RS was the first project together, and this was the second. It's been it's taken a while. I think we started 3 years ago. First 3D print was like 2.5 years ago. So it's many iterations. Yeah. Lots of work.
That is a lengthy design process. But yeah, that's interesting. We'll delve into all that because, yeah, you've been 2.5 years working on this, and I think, guys, you've done the opposite of what many other brands have done. Aero seems to be back, and dedicated Aero bikes seem to be alive and well at Colnago. That's bucking the trend of one bike to rule them all that we've seen elsewhere.
Yeah, probably we're going in the opposite direction of the others, but we do that because we found there's a way to make better bikes. So we were just not trying to follow the others. We were just trying to do our best. Someone says we are late. Maybe we are just anticipating others. Time will tell us what's happening. I have to say that the UCI is giving us some opportunities, let's say. So we just try to take those opportunities. So without those opportunities, it wouldn't have happened.
It's interesting, actually, because I find myself quite often writing, since the UCI relaxed the aspect ratio rules in 2021 and some other regulations around frame design, that manufacturers are freer now to design new bikes. But then the other explanation we hear is that racing is getting faster, and so we need aero bikes for racing. I'm guessing it's a combination of both, but can you, is there a weighting to it? Is it the UCI rules permitting aero bikes to return, or is it purely from demand from higher speed racing?
Honestly speaking, I don't think that the UCI has planned to release new rules to give us freedom to design, or definitely the UCI is not releasing new rules to make the bikes faster. That's out of discussion. I think the UCI is just trying to revise the rules to make it easier for anyone to design bikes, because as you ever spend some time reading the UCI rules, you understand very well it's not very, very clear situation. And once you relax the rules to make them more clear and easy to understand, you open windows to something different. And I think we just took that opportunity to make that. Yeah, definitely. Going back to your question, races are faster than ever. I think this year we got the fastest ever.
Fastest ever everything.
Yeah, basically. And the way they're racing also changed a lot, because till a few years ago, it was not usual to see a rider attacking 100 kilometers far from the finish line. And this year we had a world champion attacking 102 kilometers far from the finish line. So riders are spending more and more time in the wind than before. So also the bike, the clothes, helmets are becoming more and more important aerodynamic wise. So everything is changing again. So.
And so what we're here today to discuss is the new Y1RS. It's Colnago's new aero bike. I think you're okay with me describing it as an aero bike, right?
Yeah, I'm okay with you.
It's a pretty striking design. Let's put it that way. It's unique, I'll say. I'm going to ask you a question I know you've seen online, and that is, what would Ernesto say?
Honestly, I will call him later.
Okay.
And I will pass the telephone to you so you can speak with him directly. I think at the end, I have a very good relationship with Ernesto, so he will be clear with me for sure. But I think it's not new for something like that. If you look back at the Colnago history, in the 80s or in the 90s, he released some way more extreme bike than these. Just try to Google the carbon Volo track frame, which has a very similar handlebar to this one, or the C35 mountain bike without the seat tube, C35 road, all the C42, the hour record bike of Rominger. Colnago is not new to something crazy, let's say.
Yeah, there's definitely been a few standout examples in Colnago's back catalogue.
Yeah. Just if you think about the Carbi Turbo series with the 2 down tubes, it's we've been in the wild for for a while. Yeah.
Yeah. I mean, you've got the C series Colnagos. They're staying around, and they're an evolution. You can track from C40 right the way through to C68. The V series, not as old, but you can see the representation of the V1RS to the 2 to the 3 to now to the V4RS. Where does the Y come from?
Well, the Y is something completely new. It is no link to those bikes, right?
Yeah.
But I think Colnago is a brand that needs to respect its history and heritage, but also look forward. And with some of the models, well, this one is not for everyone, but it's for a very specific use. And for that user case, we've done the absolute best bike we could in terms of aerodynamics.
And so you're not, like those older models we've just spoke about, you're not looking at those for like design or industrial design language that you can apply to?
Well, certain things. You
Okay.
see some of the junctions, and there's some similarities if you look closely. But that's the thing about road bikes. You have to look closely to see those differences, right? For most road bikes.
But you can still find a way to introduce those elements, even like we're about to delve into all the design work that went into this new Y1RS.
Yeah, I think it's a very tight envelope you have. It's but still there is human decision making in the process, and even if you look at Formula One cars, they're all different, right? They should be, if they were made by the same computer, they should look the same. But there's human decision making in the process, so that gives it a bit of that. Some differences. It's something you can bring to the table as a designer. Yeah, sure.
Let's talk about then the design of the Y1RS. It's an interesting approach you've taken. I mean, you've told us in the presentation last night that it's all in on demand from the racing riders that you've got on the teams. But how you've landed on the design is quite unique. Do you want to talk us through that?
Yeah, basically, we've always been working on the aerodynamic bike, even if we never released anything before, because we weren't able to make something good enough, let's say. So the teams were always asking, when can we have something? When can we have a bike? When can we have a sprinter's bike? When can we have an aero bike? And we were just keep telling them, be quiet. We are working on something, but we don't want to release a bike just because we wanted to release a better bike. And then when the UCI came out with those rules, we say, okay, maybe we can try a different approach. So what we did was like having a design which is data driven instead of aesthetically driven. Of course, we have Torny with us, which is helping to make things a bit better from the aesthetic point of view. But everything on that bike is designed because there is a reason. The front end with the Y-shaped handlebar, it's because we wanted to lower the head tube and thus reduce the frontal area. The back end of the bike, it's because we wanted to have more vertical compliance on the bike, and we wanted to have the top tube to flex more to give a better riding quality to the bike. So everything on that bike has been designed for a reason, actually.
Aero being the main reason?
Yeah, but we always point out that the biggest aerodynamic feature on a bike is the rider itself.
Okay.
So you can have the best ever aero bike, but if the rider can't keep the aero position for long, it's completely useless, because at the end of the day, if the rider has to move on the saddle because he has a back pain, or he has to raise the hand, the elbow because he has pain on the neck and so on, it's completely useless. So the comfort on aero bike, it's even more important than on a climbing bike, let's say, because we need to guarantee the riders to be able to stay in that position for a long time. Just imagine, I always point out the ruler of the team, like Mikkel Bjerg or Langen, or those guys that are pulling for flat stages of the Tour de France for 100 kilometers or something like that. They have to be able to stay in that position as long as possible. And so comfort, I don't like the term, but comfort is very important on a road bike as well, on an aero bike as well.
What you're referring to there is that the new seat post design, the Y shaped it. I mean, one question is why?
Why not?
That's not the answer. I need to know what's the thinking behind this.
Yeah, technically speaking, we want to guarantee a more vertical flexibility on the frame, vertical compliance. But if you go straight, you can't have that one. There are a couple of aero bike, very good, very, very good aero bikes out there with a more vertical seat post, and the vertical compliance is compromised by that choice. So our idea was, okay, if we make it more slacked down, it can flex more. We went more into the details on that, and it's not just the seat post that is flexing, it's more the top tube close to the seat cluster. And to do that, we needed to have like a very slacked seat post and connected a very rigid part to the top tube. And so the flexibility of the frame, the comfort of the frame is not coming from the seat post, it's more coming from the top tube.
So that whole seat post structure that we see, the most unique aspect of this bike, it's not an aero intervention, it's a compliance, comfort.
It depends if you ask that to me as a technical guy or marketing guy. If I have to be the marketing guy, I would say that even aerodynamic wise, there is a reason. We've been able to measure a bit of the difference aerodynamic wise in the wind tunnel without the riders on, and with the rider with the mannequin, fixed mannequin on. So there is also a bit of aerodynamic advantage there. We weren't able to measure on the road or with the rotating legs of the mannequin, so I can't say it's happening. For sure, it's not a penalty. It's a small advantage there, but definitely the main reason to go with that shape is because of the vertical compliance of the bike.
Okay. That's interesting, because I think when people look at the bike, compliance, comfort, ride quality isn't the first thing that comes to mind. It's, you look at it and you think this is an aero bike. And also compliance and comfort and reduced fatigue, it's not really something that you can measure. So that it seems to be, it's definitely something that really matters. How do you measure if you're delivering on that? How do you convey that to the riders? How do you know if it's even worthwhile?
We have our own test in Colnago headquarters, where we started working on this with the V4RS. We weren't satisfied by the standard ISO test or the standard Zedler test, which is the reference in the market for stiffness measurement. We weren't satisfied with those tests, so we went more deep into the details, and we found a way to measure the stiffness of the frame in a different way. So we applied loads in different way, or different angles, with rotating handlebar, like what's happening on the road actually. So we are able to measure something. Then it's probably way more important than measuring in the lab is the feedback of the riders down on the road. And we are very happy to have our teams backing up. So we have two of the best teams in the world. Actually, the male team is the best in the world. The women team is growing. We have some new amazing riders this year, so it will be even better for the future. But those two teams are really helping us to develop better products. The guys are spending their life on the bike, so at the end of the day, they are the first tester for our products.
Just talk to me a bit about that, the stiffness testing. Like, I know you've got different aspects. You've got a seated test and a sprinting test. Just explain to us how they work in a bit more detail.
Well, basically, like the way the stiffness has always been measured, and it's still measured even by ourselves. It's just applying some loads and measuring the deformation or deflection of one part. In the case of bicycles, we were used to apply loads on the pedals and to measure the deformation at the head tube or at the seat tube or at the bottom bracket. That's not exactly what's happening on the road, because the pedals are rotating, so you have different angle of the forces applied to the frame. More important, the bike is being rock and rolled continuously during a sprint or during a normal pedaling situation, and the handlebar is rotated as well. When you sprint, if you look carefully at the slow motion during a sprint, you notice that the forces are not exactly like what you see in the Zedler test or standard test on the bicycles. So what we did is to create a jig where we can apply the loads in different angles, and we can rotate the handlebar a bit. We can apply or not the loads on the saddle, and then we take measurement on different parts of the frame. All those angles and all those different loads on the bike, we create a matrix, and we are working, or we have a formula where we can like sum up all those deformations to understand, to have a number that gives us a better idea on the stiffness of the frame. We can compare the matrix of different frames, or we can compare the matrix with previous frames. And at the end of the day, what we found was pretty curious. We were actually doing bikes less stiff than before on Zedler test, but the feedback of the riders is the bikes is stiffer because it's more target to what's actually happening on the road. For example, the V4 is not as stiff as the V3RS on the Zedler test. But if you ask any of the single rider what you think about this bike, they will all tell you, it's much stiffer than the previous one.
It's interesting though, like, I wonder if you took your test and your test results to another manufacturer and if they could set aside their bias towards their product, which is totally understandable. I mean, would they accept the stiffness test that you're doing? Would they say, no, the Zedler is the industry standard, and on that you're not comparing with?
The Zedler is the industry standard, and we are always using the Zedler to start with. That's out of discussion. But if you want to better refine the product, you need more information, and you can't simplify everything every time. So
is there a risk those types of quantitative testing that you can fall into a trap of making a bike to pass a test rather than making a bike to win a race or ride well or something like? Well,
definitely, it happens more often than what you think.
Right. And is your new approach to testing then, is that just another opportunity to fall into the same trap, or is there something about that?
I think the trap is the opposite one here because it's very time consuming. You just risk you don't have a trusted model. That's what happens. So you need first to build a model. Like the aerodynamic testing on this bike, we didn't have any reliable model. So we spent most of the time of the develop of this bike to create a model we were able to trust. It's the same for stiffness. When we started this journey, on our own testing method, we spend most of the time to try to build a reliable model and some data we were able to trust. Once you have those models, once you have a data you can trust and some target stiffness, some target reference things, then it's just a matter of keep evolving those things.
You mentioned pressure gauges there and the aero testing development work. What I understand is that you've attached a whole lot of pressure gauges to a prototype 3D printed frame, and then you've done some CFD analysis and you've ended up with a new bike. Is there any more detail?
Bit of the opposite. We everyone in the bike industry, as far as I know, are doing CFD testing on bikes and components on. We were doing that the same as well. Our previous bikes were all tested with CFD, and then when the prototypes are ready, you go into the wind tunnel. The problem is every time we were making CFD testing, no matter how accurate they were, no matter where we sourced those tests, we never found a good matching between the CFD and the wind tunnel testing. So on this bike, we decided to have a more data-driven approach to validate first the CFD model, and only then going into the wind tunnel with different prototypes. So what we did was basically do CFD test on different combination of parts. We create some 3D printed frames where we were able to swap those parts. So we were able to test different combination in the wind tunnel. The same combination we tested with the CFD, and we compared those results. And we were around 30% of discrepancy between the wind tunnel and the CFD, which was definitely not enough. So we sat down with our partner, which were at the time Khalifa University in Abu Dhabi and Polytechnic of Milan. And we asked them, why are we measuring something different? And everyone was saying, because the CFD is not accurate enough. The wind tunnel is not lying because it's a much more controlled environment. So it's something you can measure day by day, the same thing. And so how can we refine those things? And so we came up with this solution, which is quite often used in aerospace industry and automotive industry. So we were actually drilling holes in the frame, literally drilling holes in the frame, measuring the pressure in many points of the frames and comparing those measured pressure to what we had in our CFD model. And we found that the difference was high, but we were able to refine the mesh, changing the type of the mesh and changing the condition of CFD to lower that difference down around 15%. It's not what we want. We want to refine even more. because we are engineers first. So we want to go ahead with this. It will take more time for sure, but at least we had the numbers that we were able to trust. And only after having this new model, we were able to test different products with knowing that what we were testing the CFD was actually more reliable in real life.
It's something I asked you yesterday was the current model there's an error of 15%, and I was kind of wondering, how do you measure an error? Can you ever get to 100%?
Actually, pretty hard to.
Yeah.
The literature says you cannot go to 0% difference. Actually, we know there is an error, but we don't know where and why. That's a big question. And
But that 15% error that you referenced, that's like you run a CFD model, you do a test on the same model in the wind tunnel, and then you can expect to see a 15% variance. Is that what you just don't know where the variance?
15% is an average.
Okay.
So sometimes we are closer, sometimes we are a bit further back. But you can refine, but you don't know exactly why there is that 15%. So what you can do is like trying to adjust the mesh to have something closer to that thing, and to adjust the type of mesh, to adjust the conditions to get closer. But we also need more data to do that, to understand why, for example, in one part of the frame is 15, on another is 5, on another is 20. So we need more pressure point to understand where the thing's going worse or better.
One thing I've never quite got my head around is what comes first. The CAD design, the concept in your head. Like if they're doing all this CFD work, how do you then build in the industrial design? Do you do the industrial design before the CFD work?
Well, it depends on the project, but for most road bikes, you know roughly where you're going to land with the silhouette. This case was different. So I think the first couple of months, 2-3 months, we were just experimenting a lot with just trying to understand the new UCI rules and see what is possible to do from a silhouette point of view, and then evaluating all those different possibilities to see whether they make sense or not from a structural point of view, from an aero point of view. So this was a bit of a unique project in that sense. Yeah.
What I'm not quite understanding is, where do you draw the line? It's like, at what point do you start the CFD testing? And
very early on.
Okay.
Yeah, even but these days it's much easier to generate 3D models than it used to be in the past.
Okay.
20 years ago, it used to take a while to have one model, and that was the model.
Okay.
You had. And you would work on sketches before that, right? Now we just start off with modeling. Well, basically.
Okay.
Very little hand sketching, or you need to have some idea of what you're going to model. Mm-hmm. But you have the input of what sort of tube sections that we know quite, we have a pretty good idea before we start that. So and then we try out these different models, right? And analyze them from a structural point of view, but also in this case, much more from an aero point of view, if they make sense or not, right?
And so is it the case then that you never actually draw a line? It's continually evolving, and that you do your initial model, then you do the CFD testing, and then you did the pressure gauges, and then maybe you make adjustments to the model. And how many models and how many CFD runs can you do?
The number of just countless iterations in this case. I wouldn't be able to tell you how many times we have adjusted, and that's even after one settling for one direction, right?
Okay.
And the process has also changed so much that maybe 20 years ago you could say that was like one guy or one engineer, one designer was doing the bike. Now it's a team of maybe 5 people. It's so complex these days, so that it's never the case of that that person designed the bike. That's not happening.
And is it like you mentioned a team of 5 people? Is it like one person, your job is the down tube, the next person, your job is the forks and the head tube, or is everybody working on everything?
Well, some are assigned to analysis, right?
Okay.
And some are maybe working on a bottle cage or details, or there's just so many things to work on, right? Wow. It's so complex compared to what it used to be.
Does it need to be?
But to your point of the Zedler test, it used to be the gold standard much more than it is today. The stiffness to weight was the only parameter really that was interesting 15 years ago, right?
Yep.
And that has changed so much for a number of reasons. And but also back then, I remember I was involved in a project just to sort of prove that it wasn't telling you the full truth. And we did 2 different frames. One had a very, very stiff rear triangle, kind of a weak front triangle, and the other one the other way around. So a very, very stiff front triangle, very compliant rear triangle. And if you were to ride the 2 bikes, the one with the stiff front triangle was riding way better. It was no question. It was a much better bike.
Okay.
But in the Zedler test, they had the same result because the overall frame torsion. So testing is only, that's just you're testing one parameter. And I think from a handling point of view, the way a bike rides and all that, it's a slippery slope to try to reduce everything to like one number.
Is there a new one number emerging? Like it was stiffness to weight. Is it now weight to aero or stiffness to aero, or is it something I'm not even thinking of?
Well, Aero is becoming more and more important, so probably Aero to weight is the new goal.
Or is it weight to frontal area or meters squared or?
I don't know. The problem is measuring aerodynamic. It's not as easy as it seems.
Yeah.
So.
I'm getting the sense we don't want a single number. I mean, you've just said you don't want a single number, but I was just curious if there is a new one emerging. I want to go back to the pressure gauges for a second. I mean, I've seen the prototype frame here. You've got 70 of these
pressure
hoses running through the frame. I mean, talk about internal routing nightmares. That's
next level.
Was that done with any, did you take the V4RS and do the same, or is that?
Yes, we did the same as for the V4RS to have like a reference.
For this project, not in designing the V4?
No, for this project only.
Okay.
We started this just after finishing the V4RS project, so we didn't use this technology for the V4RS.
Yep.
But since the V4RS is a, proven frame or proven product for us, has always been the reference for stiffness, for comfort, for performance in general for the team. So we used that as reference for aerodynamic testing as well. As we discussed it yesterday, you even saw a prototype in the wind tunnel with the rim brakes lever for that reason, because you need to have a reference point to start with. And the V4RS has been the reference point for all the testing and in the very, very beginning phase. Then once we had something more in line with the competitors, we went through comparison with competitors' bike. But for sure, the beginning of the study were against our very own bike, where we had a CAD design, where we were able to do CFD design. The V4 was the initial reference.
Okay. And what are you what information are those pressure gauges giving you?
The pressure. Yeah, that's all information you'll get. But it's very important because the drag is actually a difference of pressure, so you need to have that.
I think that's what I'm asking. You had pressure gauges on the forward-facing edges and also on the trailing edges,
on the trailing,
and then you're measuring the differences.
Yes and no.
Okay.
What we needed to was not to measure the difference between 2 single points. The goal was to have point measurement and to compare with what we had in the CFD model. So we weren't able to calculate the drag of the bike with the pressure gauges we had, but we were able to use those data to compare with the CFD model. Sadly, you can't use the pressure gauge only because you have only a point pressure. So you have either to fill the bike with holes if you want to have a clear vision on that. But thanks to those 70 points, we were able to put those 70 points in the CFD and to say, okay, the point number 67 is giving me 2.0 and the CFD is giving me 1.9 or something like that.
And then you adjust the CFD.
And then we went back to see how we can tune the CFD to get closer to that number.
Is I mean, are you aware of any other manufacturers doing something like that in the bicycle industry? It's common enough in automotive.
Automotive is more often. Bridges are always built like that because aerodynamic on the bridges are more important than, well, you can Google Tacoma Bridge.
You're not trying to make the bridge faster, you're just trying to keep it upright.
Actually, yeah. And train and automotive industry in general. I'm not aware about anyone doing that in the frame manufacturing or bicycle industry. But I've been part of a test on helmets with the very same solution in the past. Okay. So I know someone did something similar, but I don't know if anyone did on the frames.
And like probably a bit of a stupid question, but does like the learnings from that, does that only benefit Colnago, or does that benefit CFD industry in quotation marks?
I don't want to to push that far. For sure, it's benefiting Colnago not for this project, but for the future, because what we learned is just the start of a journey for us, because we have so much data that we weren't even able to analyze before the releasing of this bike. So the next few projects will use the very same data. About the industry, probably someone will take this approach in the bicycle industry. I don't think that the CFD industry will change his mind based on what Colnago is doing.
No, yeah, I specifically meant in the cycling industry. Is there anything on the bike that you can point to and go, you know what, we learned this, which led to that intervention on the design?
There's not a single point where we addressed that. I think the most important part where we had to revise completely the shape is the nose of the fork. Okay. And Torny knows, because he had to redesign 10 times or something like that, because we were looking at some stagnation point there that we wanted to remove and that's, if you look at the prototypes with the pressure sensors, it's exactly where we placed the sensors. So we were able to measure in the wind tunnel what was happening there.
Okay. And yeah, it doesn't tell you what to do, but it helps you refine your model.
It tells you it's wrong.
Yeah.
It doesn't tell you what to do, but it tells you that you are doing wrong.
What was that process like? You've got a bayonet fork here. The intention, I'm guessing, is to reduce the frontal area of the frame. It's not a new concept, but is it still difficult to implement?
Well, it's more complex, yeah, for sure. But I mean, again, this was very much driven by aerodynamics. So if that's the solution we need, then let's go with that.
So then you took it to the wind tunnel then. After you've done all the CFD work, you've done the design work, you've now, how many iterations of prototypes did you have?
Actually, it's better to not count.
Okay.
And
there was a lot of prototypes.
There's a lot of prototypes. What I can say, and I showed you in the camera last week, we went even more forward, and we opened molds of some of prototypes, because one thing is to test in the wind tunnel. One thing is to do finite element analysis on frames, but then you never know what really happens down on the road. So we even opened some molds, and we made some frames with a slightly different shape to test on the road and to test on our jigs to understand what was happening. If you ask me how many prototypes we tested in the wind tunnel, with all the combination, it would be close to 50 or 60, something like that. We did 2 prototypes, 2 different carbon fiber, fully rideable prototypes. But yeah, countless hours on the CFD for sure.
Yeah, and the whole team got to go to the wind tunnel a couple of times, just to be able to see that if you have 2 different prototypes that are almost the same, that the differences can be pretty big, just so that everybody understands that we're talking about millimeters here, right? Small changes that can have a big effect. And I think that was really helpful from a learning point of view for everybody, just to see that in the wind tunnel.
That's what I'm interested in, actually, is like you've done the CFD work, you've done the prototypes, you're in the wind tunnel. Does it still evolve from there, or is when you get to the wind tunnel, are you then just looking for how much faster is it?
Oh yeah, but I mean, in this case, we had the wind tunnel pretty early on in the process.
Okay.
So several iterations, and you saw that model where you could also change some of the sections and replace them with a different fork section, a 3D printed one. And so that was quite early on in the process. and then several visits.
Just think about the wind tunnel is just a scale at the end of the day. So like a normal scale, it gives you the weight, doesn't tell you what to do to get lighter. So the wind tunnel is the same. It just gives you the weight of the aerodynamic of the bike, but it doesn't tell you what to do to be lighter. The pressure mapping somehow tells you where the weight is or where you can fine tune something, but it's just a scale at the end of the day. So you need to be able to read those numbers and to understand what to do later on.
Okay, folks, that's where we're cutting off the free version of this podcast this week. Just a reminder, if you head over to escapecollective.com/member, you can sign up now and you can get the entire podcast uninterrupted. You'll not have me butting in to cut you off or to remind you that you're not yet a member. And in doing so, you will be helping to ensure this podcast continues for many more episodes and months and years to come. So head over escapecollective.com/member now to sign up to Escape Collective and to get the entire episode